Hello. Now let us talk about analysis using nodal techniques. It's also called nodal analysis. And this is basically because we're going to choose a node or a point where different legs or different branches of the circuit converge, because that would be a point where a common voltage or a common current could be determined. So let's start by showing the objectives of this lecture, which are to determine, to be able to decipher what are the places where you can place a node or use as a nodal point for your circuit. Also, to be able to successfully pick the references for the voltages that you want to use throughout your computation. Remember that the goal of a nodal analysis is to be able to set up a system of equations where you can find the voltage and the currents throughout the circuit. Also, we want to review the Kirchhoff's law for AC circuits, and of course, review how to solve the equations that you get from the nodal analysis. So let's start by looking at an example where we have a circuit where the source is a voltage source, has 12 volts with zero phase offset. There's a resistor with 500 ohms or 0.5 kilo ohms. Resistor 2 has 2 kilo ohms. It is a ladder network because there's an inductor connecting the top part of the branch with ground, and this, we don't know the value of the inductor, but we know that the reactance due to the inductor is 10 kilo ohms. And at the end, the important thing is to know that we have to go to the impedance or admittance, because this is how we can relate to Ohm's law to find the voltages and the currents. Notice that we have another capacitor, or we have a capacitor with another reactance, and this is 5 kilo ohms. And then we have another active element, or a source of current, which has 4 milliamps at a 0 degrees phase shift. So if you were to find the reactance and the impedances of this particular circuit, you know that you cannot combine things in parallel and series because it's a ladder network. Therefore, what you can do is find the impedance of each element, which we can do by getting the reactance into the impedance. And we know how to do this. We simply know that the reactance of the resistor is going to be the value of the resistance. Since the inductor is not connected to anything else, is going to be the impedance is going to be the value of the reactance, and etc. So we have the voltage source, the current source, and we have the value of the impedance everywhere through the circuit. So now the next thing we need to do is find the points where we can find our voltages from the nodal analysis. So notice that this point right here has all three loads converging, and this point right here has the source and these two loads converging. Before we did the mesh analysis, which was basically internally going each mesh at a time. Now we're going to do something similar, but instead of going through the mesh, we're going to go through the nodes. So this is going to be voltage 1, which is going to be similar. This is going to be the voltage driving this circuit right here. Voltage 2 is going to be driving this circuit here, and there's going to be a combination of voltage 1 and voltage 2 in this part right here in the middle. So the first equation will be for this part of the circuit. So we know that if we cut this right here, we know that for this particular part, we have the top potential, which is V1, minus E, minus the source, will be the total voltage in this leg divided by the impedance, because we're trying to get in terms of current, electrical current. So this is Ohm's law, the top potential minus this initial voltage divided by the load is going to be current number 1 through this circuit. Okay, so that's what we have here. This is to find the current at the first leg. Then we know that the voltage is connected to ground through this load. So basically V1 minus 0 divided Z2. So we don't have to write down the 0, but just V1 divided by Z2. And then for this particular part of the circuit that we choose, but basically we have to choose after the load, right? Because we want to combine the load. So for this particular part, for the circuit on the left, we break the circuit after Z3, and then when we do the second half, we break the circuit after Z3. And I can draw again. So for the first part, we're gonna get this leg with the resistor or the impedance, this, and we cut it right here. And then here, back to the source and connect to ground. So we said this is Z2 and this is Z3. This is basically what we have. We cut the circuit right here, we cut the circuit right here, and we say, okay, from this point to this point, what we have is V1 minus V2 is the potential in this leg right here, divided by Z3. So V1 minus V2 divided by Z3 equals 0. So now we have the current through each leg. We have this current, and that current. So applying Kirchhoff's law, we found that at this node, there are 3 currents. One from here, one from there, and one to the ground. This one is V1 minus E divided by Z1. This one is V1 divided by Z2, and this one is V1 minus V2 divided by Z3. All that equals 0 because we're applying Kirchhoff's law and conservation of charge. And then we know that there's a 4th current, which is the one going over here. It's going through load 4, because this current is given, is just I, or if you want I0, whatever is simpler to remember. So we have I1, I2, I3, I4. Okay? And notice that so far, we can do a combination of equations so that even though we don't know any of the currents, except for this one that is given, we only have 2 voltage unknowns, V1 and V2. So we can set up the equation in terms of voltage. And that's what we're doing. We have equation number 1. And then for the second part, we know that, as we said, we can break the circuit from here all the way here, right? So the first thing we know is that, okay, now this is going to be my high potential. So V2 minus V1 divided by Z3 is going to be right here. And V2 divided by Z4, because the potential is the top part going through Z4 to go to the ground. V2 divided by Z4, let's go right here, plus the current that is given in the problem, plus current equal to 0. So notice that we have now simply to get the terms that are similar to get things easier. So we have V1, V1, and V1. So we can do V1 multiplied by 1 over Z1 plus 1 over the impedance 2 plus 1 over the impedance 3. And then the bottom equation, we can do V1 divided by Z3, which is what we have here. And we have V2 divided by Z3 and V2 divided by Z4 is right here. And the plus and minus, the positive and negative, is just reorganizing the equations. That is something that is just algebra, so I'm not worried about that. We know how to do that for sure. So for instance, if you take V1, Z3 to the other side of the equation, etc. Notice that on the top part, we have negative V2 divided by Z3, which is what we have here. And we already mentioned that V2 is multiplying 1 over Z3 and 1 over Z4 for equation number 2. Now, the independent values of the source and the current are right here. We know how to do this part too. So at the end, we're going to get two equations, two unknowns, V1, V2, sorry, V1, V1 multiplied by all this thing, and V1 multiplied by 1 over Z3, and V2 multiplied by 1 over Z3, and V2 or negative multiplied by all that part. This is equal to E over Z1 and equal to I. So you know that what I wanted to do next was showing you how to solve the system of equations. So you can use MATLAB or your calculator or Python, or even you can go online and ask for a system of equations, because the system of equations is basically going to be, the first part is going to be 1 over Z1 plus Z2 plus 1 over Z3, and bottom is going to be 1 over Z3, and then here is going to be 1 over Z3. So this is going to be values that you get, right? Because we have the values of all of the impedances. Z3, 1 over Z3 plus 1 over Z4 multiplied by 1, B2, V1, V2, and this is equal to E and I. So definitely getting a little convoluted there, but the point I'm trying to make here is, if you let me write down on top, is that you're going to get a number here, A, a number here, B, C, D, times V1 times V2 equals E and I, right? Or E divided by Z1. This can be solved with linear algebra method. So once you get V1 and V2, that is the solution to your problem. So this is how you use the nodal analysis. Another example would be, if you remember, we can also say that problems where you have a source connected to a load in series can be simplified to the value of V equals ZR, or sorry, IR, where R is Z. So V equals IZ, or I equals Z over V. We have V is E and Z we have it because it's given by the value of the resistor or the capacitor or whatever it is, the impedance. Once you have the current, you can place it here, and then the value of the load placed here. So you can you can simplify this circuit by writing it like this. And now this whole part up top is going to be the voltage 1, because remember, in parallel, voltage through the legs are the same, and this whole thing is going to be ground. Whereas here, this is going to be voltage 2, and as always, we're going to break the circuit here to the right before that, and then here to compute the rest over here, because this part will be the connecting part between the equations. This will be V1 minus V2, and then this will be V2 minus V1, etc. So, for instance, in this particular case, you can get that the current I1 goes up to here, then you have another current here, another current there, another current there, and another current there. So it gets pretty complicated, whereas if you do, in this particular case, you can do V1 divided by Z1, because it's going to the ground. This is going to be this current, and then you're going to do B1 divided by Z2, because the voltage through this leg is the same since it's in parallel. And then you're going to do V1 minus V2 divided by Z3 plus I current source equal to 0. Once you do that for the other side, which is going to be V2 minus V1 over Z3 plus V2 divided by Z4 plus I, which this I is not the same as this one is I naught, this one is I1. Once you do that, you're going to get a system of equations. When remember, the admittance is 1 over Z1, this is 1 over Z2, this is 1 over Z3, this is 1 over Z3, this is 1 over Z4, because 1 over Z, 1 over impedance is the same thing as the admittance. And if you notice, then we have the sources here, and then you get to the same point. You get the values of Y1, the admittance of 1, 2, and 3, then admittance 3, and then your constants here times V1, V2 equal to your currents. And then you can use Excel, even Excel or calculator, MATLAB, whatever, to solve for the voltages. So this is a very simple approach. I like using the nodal analysis when there's a circuit like this, where there's only one circuit on top to combine both voltages, because if you notice, everything else is in parallel, so all the voltages going through these branches are going to be V2, all the voltages going through these branches are going to be V1, and then simply this one is going to be V1 minus V2 divided by Z3 for the current. So that's a simple approach. So putting some numbers to look at the actual example, we have the same case here, that this could be combined into a single impedance. We know square root of R1 plus square root of the impedance. This will give us Z, and then this one is in series, the load is in series with the voltage source. Therefore, we can compute the current by saying Ohm's law, where I equals Z over V. V is the initial voltage, Z is the impedance. Once we have I, we can get that into this network, where we have the current and then we place the load up here. All right, so we can actually say that if you notice, the voltage here is going to be the same, the voltage here is going to be V1, the voltage 2 is going to be here. So to give you some values, here are all the impedances, and here are the initial sources for voltage and current. So it's the same thing as we did before, where V1 is multiplying the admittance because of load 1 and the admittance because of load 2, and by combining factors we get the admittance here. Because this point is exactly the same, this is going to be V1 minus V2 divided by Z3, right? Because the first circuit is going to be this. And then the second circuit is going to be V2 minus V1 divided by Z3, and then plus V2 divided by Z4 plus I1, and then this is how we get this equation right here. So once you solve the equation, you pretty much have the currents for each leg. And of course the unknown is the voltage, so that's precisely what we want to solve for V1 and for V2. So all this can also be applied to a very common network called a bridge network, which are very common and very useful in terms of analyzing signals or for acquiring a signal. So as you know from DC lectures or for DC content, the bridge network is an excellent network to precisely determine the variation in frequencies. So if your resistor is a resistor that gives you, or if you have a sensor that is resistive by nature, like a temperature resistor, or it's called RTD because it's a resistive temperature device. Say your RTD gives you change in resistance with time, with temperature. So at a certain resistance is a low temperature, when you increase resistance is high temperature. That's how you measure temperature in a lot of cases. So you can say that this particular one is your sensor. So whenever the temperature changes, the resistor changes, the resistance changes, and values can be acquired. Of course, that is more useful for DC applications, but in AC you can still have this configuration. And the same thing applies for AC. In this particular case, it's easier to do a mesh analysis because you have this mesh for and second mesh and third mesh when you have three unknown currents. So if you go one by one, you'll see that for mesh one, you have from negative to positive is positive voltage. Then you have E1 is going through load 1 and E1 is going through load 3. So this is this. And then E1 is also touching or also contributing for the mesh where current I2 is performing the circuit or being part of the circuit. So in this particular case, I2 has contribution on Z1, and that's what we have here. And in mesh analysis, remember that you change the signs. So if this is negative plus, now this is going to be negative here and plus here, right? So it's depending on where you have your signs. So in this case, we said this is negative and this is plus. And then we said, okay, well, in this particular case, we're going to have I2 going through Z1, which is what we have here. And then also Z3, which isn't contributing for current 1, has contribution for current 3. So I3 goes with Z3 here. So that's equation number 1. The source is part of the first mesh. For equation number 2, you have E2 going through Z1, Z2, and Z5, which is what we have here. And then you also have that Z5 has contribution for I2 and I3, so we're going to have Z5 contribution I3 and Z1 contribution with I1. Okay. And then here we have that the current for mesh 3 has contribution of Z3, Z4, and Z5. So no surprise at all that you see that here. And then Z3 has contribution with Z1 as well, so that's right here. And Z3 has contribution with Z5. So if you were to solve this equation using linear algebra and you build your matrix of 3 by 3, be careful because you're going to have A, B, C, D, E, F, G, and etc. H, I, you just have 9 values. But you have I1, I2, and I3 equal to your voltage E, 0, and 0. Notice that you have to be careful because I1 has to be organized on this column, I2 goes on that column, and I3 goes on that column. So you have to be some rearranging terms here so that I1 goes where it's supposed to be going. But other than that, you just solve the system of equations like we have been doing. Also, in AC circuits, we can have delta Y configuration, which is very common for three-phase power systems, like motors, where this example right here, or sorry, not example, but illustration right here shows you that if you have a configuration in delta Y, so delta being from A to B, so this is, if you let me redraw, this is your delta configuration. And in this case, it's upside down, but it's okay. And this is your Y configuration. So you can always go from one to the other by following this set of equations. So if you have a delta configuration and you want to go to your Y configuration from it, and if you want it to be analogous, you have to go and compute Z1, Z2, and Z3, which are the ones for delta, for Y. Remember, this is 1, 2, and 3 for Y, and A, B, and C for delta. So we have Z1 will be ZB, ZC over ZA plus ZB plus ZC. And that denominator is the same for everything. It's just the numerator that changes if you want to go to your Y configuration. If you want to go to your delta configuration where you have A, B, and C, then you're going to have this set of equations. Okay? So it's just a matter of being careful and being able to plug the values correctly in Excel or in your notebook. Be careful because these are phasors. Remember, these are impedances. So they have a value and an angle. So be careful how you compute these numbers because they can have different phases. And they do indeed for a three-phase system, for instance. So this is one example. If we have a configuration with, we have basically two deltas here. One is the upper part, one is the bottom part, and this is kind of like a network of a bridge network as well. We have a capacitor on the top part, and we have resistors on the bottom part, and the connecting branch is a resistor and an inductor. So first, this part can be rewritten as the inductance, as the impedance of the capacitor, the impedance of capacitor A, B, and the total impedance of the leg C, which is the resistor squared plus this inductor squared. The reactance of the value squared, you get the total impedance. And then from this particular case, we can get a Y configuration. So we just saw how to do that. We go to Z1, Z1, Z2, and Z3. And be careful because Z1 is the impedance connecting the dot or the point between C and B. So you have to name it correctly. And Z3, the impedance 3, is the point connecting the impedance B and the impedance A. So for instance, in this case, impedance A and impedance B are right here at point 2. Therefore, this is going to be my Z3 coming from point 3. Okay. And make sure that you do the same thing for the other ones between A and C. So between A and C, we have here this point, C connected to A, and then we have impedance 2. And it's exactly what we have here. Once you do that, which remember they're phasors, so careful how you compute them, you have the equation right here, which in your calculator you can just type them like this with imaginary numbers, positive real and positive real number, negative numbers, the same way you have it here. And this gives us a 4 ohm impedance with a 16.13 phase shift. Z2 is the same thing, you just plug in the numbers and it gives it's going to give us 4 ohms with 16.13 similarly. And Z3 is, I need to double check this one, I think there's a typo here, but if you redo the numbers here, you can compute this number right here very easily. And then Z3 is going to be the value of all this expression, which is negative 1.92, negative 2.60, negative 2.56 imaginary, because remember, this is a phasor. All right, you can change, you can turn to basically take it into a phasor form by doing square root of each element. But the point here is that we have Z1, Z2, and Z3, which we'll plug in right here. And now we can go to the rest of the circuit and notice that Z1 and Z4 are connected in series, so we can just add them up. And Z2 and Z5 are connected in series, so we can add them up. Adding phasors, because if you have different phases, you have to add the phases and multiply the amplitudes, you know that, right? Now we're gonna get a circuit where Z3 is in series with a parallel configuration of these total impedances. And this is what we have here. So if you notice that Z1 plus Z4, which these two guys, we have a total impedance of 5.8 and 1.11. And then we have, so basically this one we have 5.8 and 1.11. We have a phasor right here. And Z total for Z3, the total impedance for the third configuration is going to be 1 and 2, where basically we're gonna have these ones. Oh, sorry, this is the first we have to do. We have 2 and 5 in series. So once you do 2 and 5 is basically this right here, 6.84 and real and 1.11 imaginary. So there's gonna definitely showing that there's the same phase shift. Well, we have to compute. You know how to compute this. Is going to be tangent inverse of y.1.11 over 5.84, and this is tangent inverse of 1.11 over 6.84. So they're not exactly the same, but they're pretty close. And then the total impedance is going to be, we connect Z3 with a resistor here, or an impedance there, an impedance here, and this one will be ZT3 connecting 2 and 5, ZT2 connecting 1 and 4. Then we have that these two impedances are in parallel, and then those would be in series with Z3. So in other words, we compute the parallel resistance between 2 and 3, and we get this value. So that's the way to simplify the circuits to also compute the total impedance if you need a total impedance value for getting the Ohm's law for current and for voltage going into your system.